Welcome to Observability in Data Center Networks. My name is Joe Reves, and I'm a product manager here at SolarWinds. Joining me is Peter Phaal, one of the inventors of the SFlow protocol and one of the founders of the SFlow Industry Consortium. It's been my pleasure to work with Peter in various capacities over the last 20 or 25 years, and I'm very excited to have him here. We'll be discussing observability in the data center environment and how SFlow works to provide a comprehensive view of your traffic. So Peter, tell us a little bit about your background and experiences before we get started here.
Yeah, Joe, thanks very much for inviting me. It's great to be able to share my passion for observability with your audience. It's been something that I've worked on throughout my professional career. And as part of the SFlow Consortium, I work with a lot of network vendors to implement the SFlow protocol. But more importantly, I also work with their customers to use the SFlow measurements to address their visibility requirements and develop solutions. And so I'm really excited to be able to share some of the recent developments in that space, particularly around the data center.
Great. Peter, how did you get started in traffic analysis?
Well, actually, my background is in control engineering, which is why I really like the word observability, because to a control engineer, observability has a very special meaning. It's the set of measurements that you need to create a feedback system to control something. And so in the context of networks, you need to have a comprehensive end-to-end view of all the resources that you're managing in order to be able to drive automation and efficiency in the systems you're managing. And so that's been the reason why I've been working on the SFlow protocol and trying to get it so widely adopted, is because it then allows me to do the interesting things, which is to use the data and provide controls and automation.
So that extends not just to troubleshooting, but also to making decisions about application architectures and the architecture of the data center and so forth.
Yeah, particularly around the areas of like resource allocation. I mean, one of the exciting things about next generation data centers is how dynamic they are. You know, you can move workloads around, you can scale up and down resources as demand changes. But that's only really possible if you have good measurements of demand. And so that's really the control systems that I'm interested in, is having the measurements to tell me who's using what and why and when, and being able to then right-size the resources to address those requirements.
So we've seen a shift in the nature of data center workloads over the past several years. What's driving that?
I think the real starting point for that was virtualization. So once you started to move workloads into virtual machines, then the data center became much more dynamic. Suddenly you could live migrate a virtual machine from one side of the data center to the other. You could rapidly add virtual machines and remove virtual machines. And then other systems have been adapting to that. So you've seen storage become virtualized. And so instead of having a dedicated storage area network, you now have scale-out storage solutions and big data solutions that are running on the virtualized infrastructure. And so all aspects of data center operations have been altered and changed as people have moved to virtual machines and now to containers and Docker and microservice architectures.
So a lot of our traffic analysis capabilities kind of evolved from this notion of what comes into the data center, what goes out of the data center, this notion of north-south traffic. How has that changed over the past few years?
Yeah, the north-south traffic really existed because traditionally enterprises had large sort of mini computers running big enterprise applications like SAP or Oracle. And then you have your field accessing the resources in the data center. So that's the sort of north-south. You've got your customers up here and your resources in the data center here, and the traffic flows back and forth. As you move to a sort of microservice architecture or scale-out architecture, for every byte that comes into your data center, there's far more exchanged between the different service instances to access storage or access various compute and application entities within the data center in order to create the response that goes back to the user. And so that lateral traffic is the east-west traffic, and in a modern data center that dominates by a factor of 10 or more the north-south traffic. And so that's really what you need to architect your bandwidth to accommodate.
How about the move of workloads, the shift of workloads from on-premise data centers to public cloud? How does that impact the requirements for the kind of observability that we need?
Well, I think the public clouds do a pretty good job of giving you data about their systems. I mean, they're driven by their self-interest in that if they can measure it, they can bill, charge for it. Right. So for them, measurement is a profit center. But that really raises the bar. And so now your application developers who are using the public cloud have this expectation that they'll have that level of visibility and also the same level of dynamism and control that they have in the public cloud. So if they want to spin up 100 VMs, they can do it in an instant. If they want to spin them down, they can do that. And so I think that creates a lot of pressure on the on-prem IT groups to deliver that same kind of dynamism from their internal infrastructure as their customers are getting from the public cloud.
I've talked to a lot of customers who are trying to understand kind of the traffic footprint around some of their application architectures as well in preparation to make a move into public cloud. And that's been very hard to get your hands around, yeah?
Yes, and that's a particularly useful application for network visibility, because the network sees all the interactions between the application instances and their storage and the outside world. And so it gives you a very good sort of application dependency map, not just the dependencies, but the intensity of the relationships. So how much do you talk to storage? Should you be close to it? So if you were going to move an application into the cloud, there's a sort of a data gravity problem. It's much harder to move data than it is to move compute. And so you have to make sure that your compute is close to wherever you've put the storage. And that becomes very apparent if you monitor the network.
That puts some pressure, I think, on network tools vendors to kind of evolve some of their capabilities as well. And they need the instrumentation to be able to do that, yeah?
Yeah, and the challenge is really, as networks change to accommodate scale-out workloads, they kind of move from the three-tier architecture in which you have sort of an intelligent core, maybe a pair of core routers and switches that perform most of your functions, and then an access layer that really just acts as a concentration layer, so that because the traffic's just flowing north. So you don't really need much from your access layer other than to pass the data up to the core. And that's given you a really easy way to get visibility and control, because you have just a few devices, and typically they'll be instrumented and give you the features that you need to manage that traffic. But as you move to a scale-out leaf and spine architecture, you no longer have centralized traffic. Instead of having a few core devices, you now have hundreds potentially of commodity switches that are richly interconnected and provide equal cost multipath routing. And so there can be hundreds of paths between any pair of servers. And so you need to monitor every link and every switch in order to get visibility. And that's really the challenge in moving to these next generation architectures is how do you gain that visibility when there's no central place where you can tap or monitor anymore.
So Peter, in that kind of a network architecture, what are some of the unique challenges in getting that kind of observability that you need to be able to manage workflows?
Well, the first thing to do is really understand how people monitor flows today with a traditional core router or switch. And traditionally, you'd use something like NetFlow. And it's worth understanding how the pipeline of activities that create NetFlow records. So first, you're looking at packets. And typically, on a high-speed network, you'd be sampling the packets. And then you're decoding those packets and extracting features that you're going to use to build your flow record. So typically the source and destination IP addresses, ports, protocols. And that information is used to update counters in a hash table, the flow cache. And then when the flow stops, that entry in the flow cache is expired and emitted as a flow record. And so the approach that SFlow takes is to really say, okay, the switches themselves are being disaggregated. I mean, one way to think of a leaf and spine network is as a disaggregated chassis switch. So you can think of the spines as fabric modules and the leaves as line cards. And so what we're really doing is taking that pipeline and saying, okay, we'll leave the packet sampling on the devices, but we'll take the flow cache and move it off to a central software that's running on a commodity server. And in doing that, you dramatically reduce the costs because you're taking expensive resources that are sitting on a switch or router, and you're replacing them with inexpensive commodity compute and memory resources on a server. And this is particularly important in leaf and spine networks because your cost is everything. Instead of having a few devices, you're going to have hundreds of devices. And so the cost per device is very important. And so you have these pizza boxes bristling with network ports. And so high density is really important. And the real estate on the ASIC is scarce. And so you'd rather swap ASIC resources from monitoring towards having more ports, more routes, more ACLs. And you get to achieve that by offloading the flow cache. And so that has a number of other advantages as well, is that it gives you a lot of flexibility. It really creates what I would term software-defined monitoring, because now instead of relying on the hardware to decode the packets and decide what's an interesting flow, it's just software running on a server. And so as new protocols get deployed on your network, VXLAN, Genev, it's just a software upgrade rather than a hardware spin or a firmware upgrade on your network devices. And so it gives you a very adaptable, future-proof measurement architecture. And the final thing is it gives you real-time visibility, which is maybe not quite so obvious. If you think about it, you have this flow cache built on a traditional device, and the state of that flow cache is invisible to the outside. And so you can't really act on flows as they happen. You only see them when they finish. Whereas if you export the packet samples immediately, then your central SFlow collector gets to see the flows as they happen and can start to take actions to sort of mediate elephant flows, for instance. And a final thing that is worth really noting is that for counters, people would typically use SNMP from their core device. And you need counters because you want to know, I have speed, I have in octets, I have out octets, be able to calculate link utilizations and so on. But getting them via SNMP doesn't scale very well when you have, thousands of devices. And so what SFlow does is it also incorporates streaming telemetry. So the device will stream counter updates as they happen along with the packet samples. And so the collector has a real-time view of all the counters as well as the flows throughout the entire network.
So you mentioned sampling a little while ago. I think a lot of people have confusion or concerns about the accuracy of sampling in looking at traffic analytics. Can you talk a little bit about what sorts of applications sampling is best suited for?
Yeah, sampling really works well for volumetric analysis. So, knowing who's using what resources, who's stressing, you have a congested link, who's doing the file transfer that's overloading that link. And it is surprisingly accurate. I mean, the interesting thing about when you look at the math behind sampling and the statistics is that the accuracy that you get is proportional to the number of samples you get, rather than the population of packets in the network. So what that lets you do is for, say, 1,000 samples, you are able to estimate to within about 6% accuracy any parameter that you care to measure out of those 1,000 samples. And it really doesn't matter, whether you're taking those 1,000 samples from a 1 gig network or a 100 gig network, or 100,000 ports or 5,000 ports. You're still getting the same level of accuracy, and that's what really gives SFlow its scalability. It works well at gigabit speeds. It works well 100 gig and emerging 400 gig, and gives you a consistent real-time view of all the heavy hitters in your network, which is what you really want when you're doing capacity planning kinds of operations.
So I think we've done some case studies together that show that SFlow performs really well in very high load situations where you need to get an answer about what's generating the load as well. Yeah.
Yeah, it's really designed to be the last thing in your network to fail. A lot of monitoring systems can be quite fragile. So if the network is struggling, you lose access to the devices and lose access to the data you would need to troubleshoot it. SFlow is just really simple. It's data's streamed in a unidirectional UDP stream from the devices to the collectors. And so it's really the last thing that's going to go down. As long as a unidirectional packet stream can make it across your network, even at packet loss rates of 50, 80%, you'll still get really good data that allows you to understand what's going on. In fact, a high packet loss rate really corresponds in SFlow terms as just a lower sampling rate. And so it's very easy for the SFlow collector to adjust for packet loss and give you consistently good data, irrespective of how badly the network is doing.
Yeah. So Peter, how easy or difficult is it to actually configure SFlow and take advantage of this instrumentation?
Well, that's a really good question. People might be familiar with the challenge of configuring NetFlow, for instance. And so you think, well, if I have to do that for 1,000 switches, that's going to be really hard. But in fact, by removing the flow cache from the device, if you look at your NetFlow configuration or flexible NetFlow, most of the configuration stanzas are to do with configuring the flow cache. So all that goes away, and you end up with a very simple configuration that in which you just say how often you want counters and what your sampling rate is and where to send the data. And that configuration is the same for every device in your network. So it's very easy to automate and very simple to configure.
So how pervasively available is SFlow in network equipment today?
Pretty much every major manufacturer, their data center switches support SFlow. And the reason for that is because they're all using basically the same merchant silicon. So ASICs from Broadcom or Mellanox or Intel form the sort of heart of most new data center switches. So whether it's Cisco's Nexus line or Arista or any of the major vendors, it's typically like the same Broadcom ASIC in there doing the same things. And the ASIC vendors have supported SFlow for a long time now. And so it's just built into all the data center switches that are currently being deployed.
So I haven't visited sflow.org, the vendor list lately, but I think I saw something like 60 plus vendors on that list supporting SFlow. Is that right?
It's up there. I mean, there's been a lot of vendor consolidation recently, so maybe not as many as there were. But in terms of the devices you might possibly choose to deploy, any vendor you can think of, including all the white box vendors. I mean, as I said, they're all using the same basic designs, the same ASICs, same layouts. It's become a commodity. A leaf and spine switch is just a thing that you can buy with anybody's label on the front. It's going to be doing the same thing, have the same performance, have the same requirements. It really doesn't matter who you buy it from. I mean, there's some differences in, depending on which CLI you're familiar with, but in terms of the functionality of the devices, they're all pretty much interchangeable.
So the SFlow Industry Consortium really drove the widespread adoption in merchant silicon, yeah?
Yes, and those vendors are all members, and in fact, they work with this consortium to extend SFlow to export additional measurements that their hardware is capable of. So Broadcom, for instance, released extensions that get you better insight into buffer management on their ASICs, and is streamed out with the SFlow telemetry.
So SFlow also has extensible templates in the protocol, yeah?
Well, it doesn't really use templates in the same way that IPFix or Flexible NetFlow does. It has tag length value of structures, and so new structures get added to the library, and they add new measurements. So it's an extensible protocol. You don't need to upgrade to get new measurements.
And I can find those on sflow.org, right?
Yes, they're all published there.
So Peter, one of the challenges in moving to leaf and spine is that it's a fully routed network. How do we bring along some of the legacy layer 2 functionality that we need?
Network virtualization allows you to tunnel legacy layer 2 traffic over the routed leaf and spine network. And typically what would happen is the top of rack switch would encapsulate the layer 2 frame as a VXLAN UDP packet and send it to the destination leaf switch, where it'd be decapsulated by the hardware and presented to the end host. What you can also get is encapsulation happening on the servers themselves, and there, the virtual switch perhaps is the source of the tunnels and the termination of the tunnels. In either case, having visibility into the overlays as they traverse the network is really important, because if you're trying to troubleshoot a problem on the virtual network that you've created, you have to understand the paths that those packets are taking over the physical network. So you can know that, it's a problem because it's this physical link that's dropping packets, for instance. And SFlow addresses that because you're getting the packet header as part of the packet sample. And so the SFlow analyzer can easily decode the outer layers of the tunnel and the inner layers of the tenant traffic, and it gives you that visibility into the full stack. What's also interesting is that as the network edge, moves into the servers in the form of virtual switches, that you really have to think of the virtual switch as really an application running on the server. And you can't really understand your network performance unless you understand the performance of the server that's hosting that virtual switch. And so that's really what led to the open source host SFlow agent. And it's an agent designed to run on servers that monitors all the key server performance metrics and uses the same data model and protocol as SFlow from the physical switches. So you now get a sort of a consistent view of your network, whether it's running in software at the edge or in hardware at the core. And that really simplifies your management, because now you have end-to-end visibility using the same technology with a consistent set of measurements. And it extends even into the public cloud, because now you have an agent that you can deploy on virtual machines in the public cloud that lets you get the same packet flow data and counters that you would otherwise get from the physical switches. But in the cloud, you don't have any access to the physical resources, so you need to sort of bring your measurements with you. And that's what the host SFlow agent does there. So it gives you a really nice sort of unified view of all your resources end-to-end, whether they're in the public cloud, on-prem, physical, or virtual.
So we thought, I guess, historically, we've thought about flow instrumentation as being something that's only on network equipment. But as that edge of the network becomes more fluid, we need more sources or more points of observability.
Yeah, and it's really critical, because today there are far more virtual ports on virtual switches than there are physical ports. So, it's basically the tip of the iceberg. If you're not monitoring the virtual ports, you can run aground like a Titanic. I mean, it's just this huge iceberg of stuff running on servers that you really need to be aware of if you want to understand how your network is performing.
So Peter, can you sum up the benefits of SFlow in the data center for us?
Sure, it'd be my pleasure. The key benefit is that it's affordable. It's built into your equipment, so you don't have to pay extra for it. It's really simple to deploy. As we see in the configuration, there's very little to do. It's the same on every device. It's comprehensive. It's giving you all the measurements that you need from all the different devices in the network, whether it's servers or switches or virtual machines. Has a unified data model that lets you pull all this data together. And finally, it's actionable. So it gives you the key measurements that you need to take action. It tells you who's using what resource, when, and how. the kind of information you need, not just to know that you have a problem, but to fix it.
Great, thanks. You'll find some additional pointers to the SFlow Consortium in the links for this session, as well as the host SFlow project that Peter mentioned that's being actively developed, and Peter's blog that's devoted to SFlow related topics. So thanks again, Peter, for taking the time to educate us on SFlow.
Well, thanks very much. I really appreciate the opportunity, and thank you all for watching.